seepage information coupled analysis is for unsaturated river environment using please.
Thank you, Mr. Sakai. Good morning, ladies and gentlemen. This morning, I would like to talk about the seepage information coupled analysis method for unsaturated river environment using elastic model. So it means its analysis, so it includes some equations. And this is a work with my colleagues, Dr. Sayuri Kimoto, and the former PhD student is now working in the consulting company, Ryosuke Kato. Well, I will give you first of all the introduction to the outline of the course. Then go to the seepage information capital analysis method for unsaturated soil in general, and it means the conservation laws and the conservation equation for unsaturated soil. But in fact, we will use a simplified analysis method. And finally, I will talk about the numerical analysis result. It includes the validation for the experiment. And then, finally, I will go to the parametric study to evaluate the effect of some parameters. As you may know, the recent years, many flood interactions occurring all over the world, associated with typhoon, cyclone, hurricane, and torrential rains. So we have many disasters nowadays because of the failure of the embankments, and the seepage flow, the seepage flow, and the overflow. You know very well. So the right-hand side, you can see the picture in Thailand, the recent flood, and the right down, you can see the failure of the embankment in Kokuri Prefecture was 7 years ago. So we observed due to the heavy rain, the high water level of the river, we observed very large deformation and finally the failure of the river embankment. So of course we have the evaluation method or the conventional method. It includes the seepage analysis and the straight type of stability. But we use separately. We use this technique to check the whole safety of the environment. But in my opinion, we need more advanced methods to predict and evaluate the safety of the environment, river environment, and other structures. So the research on the seepage deformation coupled analysis for concentrated soil, we need more advanced methods to evaluate the safety structure. So go to the governing equations and quickly explain the main part of the governing equations for three phases. Yeah. So first of all, we need the stress value. This is very important. We use the partial stress tensor for three phases by the analogy to the saturated soil. You know very well the effective stress for the water saturated soil. So we can automatically obtain the partial stress for fluid phase and solid phase with spherical stress in magic pump. And then summing up these partial stresses, we can obtain the total stress. And finally, we obtain the relationship between the spherical stress and total stress and the average population. This is the average population advocated by Christine Yomi. She called it the average population. So this is the spherical stress. Because, in this case, we adopted the tension is positive. So the T is the pressure, so this plus sign means heat. And also we use the suction in the construction model. So it means the skeleton stress is not the effective stress because we need another variable. So that's why we don't use the technical words effective stress. So we need the skeleton stress as well as the suction. This is very important. So it's not so easy to obtain, but it's not so easy. There's several manipulations we need to get the consciousness. And sorry, I have to explain the N super S, delta, and energy are the boring fraction for each case. And then go to the well-known conservation mass for three cases with using the average density of the three phase materials with the porosity and the saturation. This is the usual. And then, of course, we did the equation motion, the conservation laws of linear momentum for three phases, water and air, with the three interactions between two phases, between the solid soil and water, and between the air and water, and finally the solid and air. But we don't adopt interaction between, for simplicity, we don't use the interaction between water and air in this case. And then we adopted the usual Darcy type of interaction, some I and Q sub I between the fluid and the solid. And the WI is a Y dot is the relative velocity between two phases. And then to the next steps, we adopted the assumption the relative acceleration is almost zero. So in that case, we can obtain a simplified equation solution for fluid gas. And also, summing up all of the three equations, linear momentum, equation for linear momentum, we have obtained. So it's, and also we adopted the acceleration of the solid phase is much larger than the relative acceleration. In this case, we can obtain a simplified, very simple equation motion for the whole mixture. So it is. And also that we need a continuity equation for fluid phase in the water and the air. And also in this case we adopted the simple elastic law for fluids. And we can assume that the K super A is the rigidity of the air is very high. The compressibility is very high. It means Ka super A equals to zero. The rigidity is zero. So in that case, we can assume that P super A, the air pressure is zero. But if we do the three-phase analysis, I observed in the usual case, it's not so large value of air pressure. So in this simplified analysis, the P super A is almost zero. Now, go to the conservative model. For the conservative model, we used the extended model. We extended the cycle to the classic model almost 10 years ago, I suppose, based on the elastic plastics theory with the generalized non-critical rule and then with the whole consolidation boundary surface. And in this case, we used the nonlinear kinematic Hagen rule. So we can apply to the cyclic behavior. And in this case, for the unsaturated soil, we consider the effect of suction, the degradation with the change of suction, the decrease in suction. For the boundary surface, that controls the yielding and the potential. It's very important. FB equal to zero. It's the surface is the stress base, and that the size is controlled by sigma and b prime. And if the bar stress sub 0, it's a relative stress ratio invariant with theta ij sub ij, the stress is relative stress ratio. Yeah. So the sigma and b prime is very important. It's controlled by the accumulated plastic strength. So it's decreasing and also increasing. It's dependent on the material parameters sigma m, k, f, and the beta. It's shrink or decreasing or expanding. And also, I consider the effect of suction. So this is this term exhibit the effect of suction. So initially the suction effect is 0 and then decreasing. Because of if the suction decreasing, infinite is 0, it means this term can see. So it means the effect is decreasing. This is very important. So the two, I will remind you the effect of the strain accumulation and the effect of suction. Later, we will. So this is the schematic figures, illustration of the shrinkage of the boundary surface with respect to the change of suction and the accumulation of the plastic strain. And also for the change of the stress ratio, we adopted this type of the functions with the having parameter, matter having parameter chi I j sub I j at risk, with two having two material parameters. A super stress is equal to the stress ratio failure, and the B is related to the plastic movements. Of course, the B is also follows the differential equations for the change. And also, in this case, we adopted another effect, the suction effect for the plastic hardening parameter B. So it's a similar type, the degradation for the boundary. And for the change of the mean effective stress, we adopted the secondary function. So it means it's non-associated. And for of course, we need a plastic potential function because it has a plastic stability. This is G equal to 0 is the potential functions with the similar, same kinematical hardening parameters, chi and j. And with the delta coefficient. It may change outside, inside boundaries of vessel opportunity or and finally we use the chip. Of course, we need the water characteristic curve as a constitutive model. In this case, we adopted a finely constitutive equation for the water saturation with the suction conditions. I also consider the effect of the saturation dependency of permeability. Well, go to the numerical analysis. First, I will talk about the validation of the model. We did the model test in the laboratory. This is the picture. It's a very small, 1 meter height of the model environment. We did the seepage test and the overflow test. Today, I will talk about the seepage. We installed the several points to the pore pressure gauge. We measure the pore pressure in time, and also measure the deformation along the surface of the heat. This is a numeric finite element measures. And these are material parameters for the soil schedules. And in addition, we assumed the smaller value of permeability for the surface of the embankment, because usually we always overcompact the surface of the embankment. This is the usual manner, because of the stability of the embankment. So there is it 100 smaller value for surface. This is the water level time profile. 113 hours, increase, and then it's constant. And the initial pressure distribution is, we assume the linear distribution of the pressure between the hydrostatic pressure to the constant suction in the environment. This is a transition zone. So this is distribution of saturation with time and the irritation line. But the less than this line, the environment is fully saturated. And then I will show you the distribution of the hydraulic gradient after one day. You can see the maximum point for 3 here. It means the back side of the environment. And this is the distribution of accumulated plastic shear strength. It exhibits the degradation of the material. So we can see the 2.45% at the top of the. And this is the comparison of the pressure and the experimental simulation. And sorry, this part is not accurate because of some measuring travel to the experiment. And of course, there is some difference, but we can see the latitude and limit. So, the trend is similar to each other. And also we measure the displacement, but this is a displacement to the normal direction, normal to the surface. And then, of course, there is the onset time is always the same, and of course it's different. But in the experiment, we observe the large deformation at the top of the environment. But in the simulation, almost same or little bit less. It's something that is different. But the trend of these results are similar to each other. So it means that we can apply the analysis method, to the another problem. We did the parametric study for the more realistic environment. The height is 6 meters, the environment, and the water increase in 18 hours. This is a final calculation. So the environment is unsaturated. At the initial stage. So we did the 8 cases in that. The first case is no degradation, no effect of suction, and no strain-induced degradation. And the first one is the degradation, the shrinkage of boundary size due to the suction. And the SV here, the case 2, the degradation, effect of suction, form the hazard boundary. And also the case 3 is just only considered strain-induced degradation. And for case 4, 5, 6 are combination. The final one is to consider all of the. But we can see the maximum after 1 day, we observe the maximum shear strain is for case 6. But I think with the consideration of the degradation, we can observe the larger value of the shear, accumulated shear strain. This is the distribution of saturation in time. Let's see now. this is here is the labor side. And this is Dutch. And we can observe the case there, we can observe maximum value of the hydraulic labor is 0.59. It's larger than 0.5. It's, so it means, with respect to the guideline, conventional guideline, is dangerous, is safe. And then we show you the distribution of the plastic shows the accuracy. For case, this is the case there, we can observe the larger value of the accuracy frame at the top of the environment. This is the little side and the right side. And the case 1 is large, more larger volume, and case 2 is more, 20% of heat. And also you can see the strain localization along the slope in the ribs. And then go to the next cases. Case 3. In this case, just we consider that the strain induced degradation. The maximum accumulated strain is 11.5. And then we consider case 4. Case 5, we combine two effects. Effect of the boundary surface and effect of the padding parameter, and this is the case, we consider the boundary surface effect, boundary surface shrinkage and strain in this degradation. In this case, we can see the very, it's not a straight line, a little straight line, discontinuity of the degradation. And the final average, this is the same one. This is the case 6. Is we consider the effect on the plastic modulus D and the stress in the degradation. Maximum value. 21.2% heat. And finally, we consider all of the degradation. So it means we can, if we consider the degradation of the materials, we will see the failure of the total embankment, and also as well as the discontinuity of the degradation strain around the slope of the levers. So finally, how do I conclude my talk? First, we did the analysis of we analyzed the seepage flow in the formation capital analysis for the test environment with the seepage flow. And then we compared with the experimental result. We would say that it's applicable to the concentrated environments with the seepage flow. So we go to the parametric studies, and we have found that the procedure, the strain-induced degradation and the change of suction leads to the large accumulated plastic strain at the top of the compartment, as well as the slope, degradation of the slope of the leaves. In particular, in the case with the consolidation of the decreasing halving parameter B, that controls all of the most, it leads to the largest strength. Over the wide and so the degradation of B is very important. But the strain and the suction of this degradation does not affect the infiltration pattern. The infiltration pattern is almost the same but the distribution of the strain is different. This, thank you very much.
Thank you very much. Thank you very much. So I'd like to put some comment from the boards. So do you have any questions, comments? Yes, please.
I'm from the Galway from Queensland Minister of Technology this day. My question is, in this upper analysis, unsaturated seabed plus deformation. So did you consider consolidation settlement which is occurring at the same time? Consolidation.
Yes.
So-
You mean the settlement of the boundary?
Yeah, in your model text, you compare your numerical results with the measurements.
No, we did not measure the settlement of the top of the boundary. Only we measured the slope.
Yeah, when you measure that on the slope, that is actually part of the settlement is due to deformation due to seepage induced deformation. Plus, then you have settlement due to consolidation also.
Yeah, but it's the base land we use the same materials, compacted 90%. Well compacted. So it's 1 for 7 meters, but it's not so much. This case is. Sorry, I did not.
Yeah, that's what I wanted to know because when you feel the river side, you took like 24 hours to feel this side. Because during that feeling, it's getting saturated, the part of the embankment. So, because embankment can set
Yes.
it's not due to only due to deformation of unsaturated slope, but it's again can consolidate. So I feel that's mainly that could be the difference. Like in the measurement, you will capture that settlement also, but in your numerical analysis, you basically focused on unsaturated deformation.
Yeah, of course, we can.
Okay.
Another question. Thank you very much. So, I'd like to move next speaker. Professor Han. He is a professor of University of Ottawa in Canada. His dissertation title is Design of Single Pi Foundation using the Mechanism of Unsaturated Solids.
I'm not seeing the screen here. This is not on. This is not on. No, no. Yeah.
So, please.
Okay. Ladies and gentlemen, my presentation today is entitled Design of Single Pile Foundations Using the Mechanics of Unsaturated Soils. Let me thank my co-author, is one of my PhD students, Neil Taylor. Prior to this presentation, we had two other presentations. One is very practical oriented, and the other one, which was by Professor Oka, he introduces some concepts related to unsaturated soils. So my topic is also related to unsaturated soils, and I can assure you this is a lot more simpler. The outline of my presentation will start with an introduction, and I will present objectives of my study, provide a brief background, and also discuss the testing program that we have undertaken, and discuss about the model pile test. Just the way Professor Oka has conducted model tests, we also have conducted some model pile tests. And as people with having experience in unsaturated soils will realize, these tests are very time consuming and very complicated. So therefore, please understand that this simple tests are not really that simple, and it takes a lot of background preparation to understand the influence of all the parameters. So after interpreting the results, I will try to extend this to a case study and then conclude my presentation. Let me provide a brief historical background about the bearing capacity of soils. So we know these are the pioneers: Carl Terzaghi, Scampton, George Meyerhoff, Alexander Westig, etc. They have contributed significantly to our present understanding related to the bearing capacity of soils and the design of shallow foundations. And we use two different approaches. One is the effective stress approach, which was presented by Carl Terzaghi, where the effective stress equation sigma dash is equal to sigma E minus UW was introduced. And later on at Imperial College, it was Scampton who introduced the total stress approach to understand the undrained bearing capacity. So we have Terzaghi's approach for the drained bearing capacity and the Scampton's approach for the undrained bearing capacity. But both these things were for saturated soils. In 1936, in the first conference of saturated soil mechanics, they understood that the soils can be in a state of unsaturated condition, but at the same time, we have some simple tools to understand the worst case scenario that the soil is completely saturated. They have come up with this simple analogy of assuming the soils are in a state of unsaturated condition. And again, the studies that were taken by the Terzaghi and Scampton were in the regions where the soils were typically in a state of saturated condition. Terzaghi did most of his work in Massachusetts, where you have Boston blue clay and the soils are saturated, and Scampton, he has conducted mainly on London clays where the soils are typically in a state of saturated condition. But let us take the real case scenario. If you try to see this picture in this bowl, we have soils which are more in a state of unsaturated condition rather than saturated condition. However, we always assume the worst case scenario that the soil is in a state of saturated condition. As Professor Oka has said, it is very important for us to understand how the engineering behavior of soils from unsaturated conditions to saturated conditions has to be clearly understood. So we see soils are in typical state of unsaturated condition in many regions. The red, yellow regions are typical examples of unsaturated conditions. To put this in perspective, I am trying to show the scenario of saturated and unsaturated soils. So typically, Carl Terzaghi has concentrated on saturated soils, but it was Bishop in 1959 who introduced the concept of unsaturated soil mechanics, and for the first time, it was Professor Fredman and Morgenstern who have introduced the concept of unsaturated soil introducing the stress state variables, net normal stress and matrix suction. Carl Terzaghi used one effective stress equation to explain the engineering behavior of saturated soils, and these people have introduced two stress state variables, net normal stress and matrix suction. Here in saturated conditions, as you can see, all the voids are completely filled with water and you have a two-phase denominator. But in unsaturated condition, you are having the voids filled with water as well as the air, and as Mr. Oka has introduced, the difference between the air pressure and water pressure is the suction, and this suction can have an important influence on the engineering behavior of unsaturated soils. Typically, we have negative pore water pressures, and the negative pore water pressure with respect to atmospheric pressure is the matrix suction. So if you have a shallow foundation, and in this shallow foundation, you will be having a stress fault that is formed about a depth of 1.5 to 2B, and in this case, you are having unsaturated conditions, and you can assume the average matrix suction value and then try to see what is the influence of suction on the bearing capacity. Our earlier studies with respect to drain loading condition and undrained loading conditions have seen that the bearing capacity and unsaturated conditions is very high. So it is 2 to 4 times. So this is the introduction that I am trying to have to introduce how we can extend the same concepts to actually to unsaturated soils in the design of pile foundations. As you can see here, we can see below the groundwater table you have positive pore water pressures, and above the groundwater table you can have negative pore water pressures. Typically, we don't have groundwater table up to the surface, and in the deep foundations, no one has taken the impact to understand the influence of suction on the carrying capacity. So with this in objective, as a key objective, a research program has been identified, and these methods are even known to undergraduate students, alpha beta method in the design of pile foundations. We try to use this methods and extend this for unsaturated soils to estimate what is the carrying capacity of the shaft bearing capacity of single piles, and some laboratory studies were undertaken, and we have interpreted and we have provided the comparisons. And we can see that there can be end bearing capacity and also the friction that will be generated all along the pile. So we have different equations, but the focus here would be what would be the influence of suction on the friction capacity. Typically, we can express the equation as Fs into As to find the influence of shaft capacity, but as you can see that this is influenced with respect to undrained cohesion, effective stress, and the delta, which is the wall angle friction between the soil and the pile materials. So these are all the concepts that we know for saturated soils. And this background information has been provided for undrained loading condition, which is the alpha method, which uses the total stress approach. So the conventional method, which we all know here, has been extended for unsaturated soils. I'm not going into all the mathematical equations, but what you can see here is the unsaturated and unsaturated condition. This is the equation we can have to estimate what is the shaft capacity of the pile, and there are two constant mu and mu, and these are explained in the paper and which is in this conference proceedings, and also more details are available in this particular paper. So this equation, even though it looks complicated, if you are having matrix section equal to 0, which means the soil is in a state of saturated condition, you will be having the same simple equation that was provided by Skempton. In other words, there is a smooth transition. Now we also know beta method. This beta method has been introduced by Chandler and Berlin from England, from Imperial College London. And again, I am not going into all the mathematical equation details. And this method is used based on effective stress approach, and for drain loading conditions, we can use it. So I have introduced the concept of shear strength of unsaturated soils into this equation and developed a mathematical expression which would be helpful to determine what is the carrying capacity of the friction point. So another approach, so this can be extended to fine grained soil too. In the fine grained soils, sometimes we can have apparent cohesion. The effective cohesion component due to adhesion has to be understood. I will be discussing that with some results. The next method is the lambda method, which was put forward by Vijayawardgia and Foch, which is in between alpha method and beta method. And again, we have an expression which has been developed, and this expression again has a smooth transition from unsaturated condition to saturated condition. In other words, the expression will be the same as the equation for saturated soils once you have matrix suction set to 0. Well, that was the theoretical part that has been developed, and we tried to test using model piles what is the carrying capacity of the pile under saturated condition and unsaturated condition, using two different drain loading conditions, drain and undrained loading conditions. In the paper, which is in the proceedings, we have tested Indian head till results are presented, but I am presenting loam soil results too. For this, we need the additional information, what is soil water characteristic curve. Again, thanks to Oka, who has already introduced what a soil water characteristic curve is. It is the relationship between water content and suction. So now, having that piece of those information, and along with using this compaction curve, we have selected 3 water contents: water content 13%, 16%, and 18%. And we measured what is the suction at this 3 water contents, and also we measured the soil water characteristic curves. As I said, this soil water characteristic curve can be used as a tool in the estimation of the carrying capacity of the model piles. In other words, once you have the soil water characteristic curve and the saturated soil parameters, using the equations that you have seen, you can find out what is the carrying capacity of the pile due to the friction with varying suction. So using a pressure plate apparatus, we can measure the soil water characteristic curve. And again, the same soil can have different soil water characteristic curves, because as you are compacting, you can have different structures, and these structures can influence, soil structure can influence the soil properties significantly. This another soil, loam. Again, this is not discussed in the paper, but I am showing you just to show that we are working on other type of soils too. Again, the soil water characteristic curve has been measured using the pressure plate apparatus. And to measure what is the suction at a particular water content, we can use axis translation technique, which has been introduced by Hill, to measure the suction. And at 3 different water contents that we have chosen, we have measured the suction values, and these suction values were as listed on this particular slide. So this is how the test has been conducted. The soil has been compacted and the soil has been saturated, allowing the water flow. And we have used tensiometers to, first after saturation, what we have done is we have assured this in different ways to know the soil is saturated, and then we have introduced the conditions to desaturate the specimens, and also we have collected samples at different depths, and that is for the drain condition. And as compacted, when the matrix suction is constant, what we have done is we have used a thin wall tube to take out the soil sample of 220 mm length, and then now introduce a pile and see that there is a void that has been actually introduced. So now this pile is actually loaded to this void such that only friction is generated and there is no end bearing resistance. All the data has been collected. And again, the tensiometers were helpful in measuring the suction. And the readings with respect to suction as well as water content were determined, and I have shown you some details of how those things have been done. And we also have back calculated this soil water matrix suction values to check that they are falling along the soil water characteristic curve. So here we have a specimen of a particular suction value, 60 kPa, and we have tested under drain loading condition as well as undrained loading condition for a water content of 13%. And you can see the shaft bearing capacity versus displacement, and compared to saturated conditions, you can see unsaturated conditions are carrying a very high load. The same thing we have done for another sample which is compacted at a different water content both under drain and undrained loading conditions. Under drain loading conditions, you have a higher value compared to undrained loading conditions. Here is a different soil, loam soil. Again, the test procedure is actually the same, and this is another one where we have varied the matrix suction, because this is the field case scenario, and we have determined for one particular water content, the soil compacted at an initial water content of 16%. So now this data of drain as well as undrained loading condition, both for Indian head till, which is a glacial till which is commonly found in Canada, and other one is a loam soil which is close to a sandy type of soil, have been analyzed using 3 different methods, which is the modified alpha method, beta method, as well as lambda method. So here after compacting, we also on the side we have taken a specimen to determine what is the unconfined compression test, and here some results are actually shown, and using the theory that I have presented earlier, you can see that there is estimated values as well as measured values. I will show you the results. Now how Cu has been estimated, we have used this mathematical equation that we have derived, and we can use the standard alpha versus Cu charts to get this alpha value, and we can actually back calculate from the pile load test this results for alpha method. And the same thing, I'm just presenting the results right now. Later on I will show the compression. The modified beta method, which is for the effective stress analysis, has also been done, and we calculated the values that are necessary for delta from interface direct shear test results. And now showing the results of lambda method, we have modified the lambda method that was introduced by Vijayvargiya and Ford, and then we have provided a relationship between lambda and delta by L, and this delta by L value we can actually get from our experimental results, and now we have provided the comparisons for the test that we have conducted, what is the estimated value and what is the measured value. So for Indian head till, again varying suction value, here are the results, estimated and measured values. But more than this, I will show you next in charts. The same type of approach has also been used for loam soil. So all the results are actually summarized here. And if you try to see here, the comparison between estimated and measured values for alpha, lambda and beta methods, reasonably okay for different values, and here it is for different soils, reasonably good comparisons. In other words, this is promising. We had some experimental problems because when we were inserting the pile, the soil was getting a little disturbed, and therefore some of the results mostly are on the lower side. So we are now using a different improved method such that this disturbance is actually reduced. So using the theory that we have developed, we have compared with a case study results, the results which were actually published in a PhD thesis from Imperial College London by George Edders. What they have done is, they have used this kind of scenario where a pile of length 20 meters and diameter 1 meter, they have varied the groundwater table, and their idea was to see how under drain conditions as the soil desaturates, what will be the increase in the carrying capacity of the pipe. So, as I said to you, the main purpose was to simulate a field condition where dewatering and drainage takes place, and during that carrying capacity actually increases. In other words, the groundwater table actually changes. Those results of a computer modeling study, finite element modeling study, we actually did from our results using a soil water characteristic curve. This is a chromatil. So we don't have the soil water characteristic for chromatil, but the properties of the chromatil are similar to the Indian head till. We use the Indian head till property soil water characteristic curve, and we exactly the same way that Georgia has done during the groundwater table. We try to use the similar conditions, and then we use the approach of beta method that we have developed. But in this particular case, because we have not yet developed the carrying capacity, end bearing resistance, so we only determine the shaft resistance, and we are providing the comparisons. And you can see that end bearing resistance in a very long pile is not that much in a till soil. The shaft resistance is the chief contributing parameter all along the length, and you can see that the results are reasonably good, but I think we are doing more studies to understand the end bearing capacity, and that would actually help to see that there is better results. So this point is the point which we have estimated, and this is from the finite element, and you can see that there is a good comparisons. So now, to summarize, we try to develop methods which are consistent with saturated soil mechanics. Alpha method, beta method, lambda method, everybody knows those things. And the practicing engineer actually likes to use the same kind of approach that is already available for them, and we develop in such a way that there is a smooth transition that is taking place from unsaturated condition to saturated condition. So that approach of alpha, beta and lambda has been modified, and we have tested for drain and undrained loading conditions and presented the approach. So we have seen that from what the studies that we have done on two particular soils, the modified approach presented for interpreting the data is working well, and there is a good comparison, and the total shaft resistance can now be understood. We are working on the end bearing capacity. So this modified beta and lambda methods are promising for practical applications. So here is my research group. I have to thank my research group for doing a wonderful job, and once again, I thank Neil Taylor, who is my PhD student, and also Professor Fredlin, who is and who was my supervisor. Once again, I will take this opportunity to thank this conference organizers who have given me this opportunity to present my research, GeoMap 2011, and also the funding that I received from NSER is sincerely acknowledged. Thank you very much.
So I'd like to move the discussion. Yes, please.
Yes, my name is Benazir from Sudan.
Excuse me.
Thank you for this interesting lecture. My name is Abdul Karim Zain from Sudan. I have one question, or maybe compound question. First of all, I would like to know what is the most reliable and practical method of measuring matrix suction, especially in clay soils. And then I would like to ask, how can you extend your work when we are working with soils with low moisture content and very high suction, matrix suction. Because I saw that the suction magnitudes you are working with is around 200 kilopascal. So in arid climates like when we have, like our country, we have soils extending down to bed depth with very low moisture content. That means that you will have very high suction values. So how can your well be extended to such types of soils? Thank you very much.
It's a very interesting and practical question. So right now we have various instruments for measuring the suction. In the low suction range, we can use tensiometers to measure the suction. And these tensiometers are capable for measuring the suction from 0 to 100 kPa. And there are also high capacity tensiometers which are said to be HCT. Those also can be used and they are a lot more expensive. And recently we have developed, and one paper has been actually published in ASTM, very recent one. We even used a pocket penetrometer in the field whenever we are collecting the samples to insert it and back calculate suction values. We can also use what is called the filter paper method. The filter paper method can also be used for measuring the suction. Another way is if you can measure the soil water characteristic curve, and when you are sampling the samples, if you get the water content, from the soil water characteristic curve, you can have the suction. But there is the effect of hysteresis. So the effect of hysteresis of drying and wetting might influence the suction value, but still, as I was showing you, even in low suction values, in sand, even if you are able to retain 2 kPa, and in clays if you are able to retain 50 kPa, and in most cases, for example, in your country, in Kenya and Sudan, etc., where the soils are typically in a state of unsaturated condition, the suctions are going to be very high, and you can take advantage, even though the suctions are going to be more than 1000 kPa, you can take the worst case scenario of 100 kPa and try to design pipes or shallow foundations.
Okay? So, as time so I move to next.
Thank you very
Thank you very much. So next speaker is Professor John. He is a university Flora Policy His presentation. So the title is Programmatic Soil in Search for Solution. Please.
Thank you, Mr. Chairman. Ladies and gentlemen, the title of my presentation is Programmatic Soil Research for Solution. Basically, I'm just going to give you an overview of some of the work that we have been doing. Thank you. So my presentation outline is type of soils in Malaysia, why soil is a problem, and some of the work that we've been doing, meeting some of the challenges. And I can assure you that my presentation is even simpler than my two honorable colleagues. Okay, to begin with, let me start with Malaysia. For those of you who have not been to Malaysia, you will know that Malaysia is a tropical country, so the climate is plus minus 20 degrees north-south of what we call the line of equator. So you can see here, Malaysia is somewhere there. I think Japan is somewhere up here, about 5,000 kilometers southwesterly, or from where we are, you are north, and from where, from where you are, we are south. Okay. So that basically also detect the type of soils that we can find in our country, which may be quite different from your country. For example, 70% of our country is covered by a soil type, which we call as residual soil types. Of course, one thing peculiar about this residual soil type, the water table will normally very deep down or very low. And as such, the unsaturated soil mechanics would be the useful thing. But of course, we been covered extensively by my colleague. And the remainder 50% of the soils is marked as what we call as alluvial soils. So basically alluvial soils are transported soils, and by virtue of those locations, they are mostly found along the coast, and these soils are often called coastal alluvium. Right? So this is just a very brief map to show the soil types in Malaysia. It's just quite simple. Along the coast, you have all the coastal alluvium marked in white, and inside in the interior, we have all this so-called the alluvial soil, which is a bit on the high ground. Okay. Now, reservoir soils are basically soils which have been formed in situ by extensive chemical weathering, because we have a very high temperature, very heavy rainfall, and typically when rain 4,000 millimeters per year. So that's the main agent of the soil formations. So by virtue of their formation, this is being left in place for the residual soil, and whose character depends on the parent rock from which the soil developed. For example, residual soil on the weathered granite will initially be sandy as sand-sized particle of quartz, and partially weathered feldspar are released from the granite. Okay? The weathering profile may look something like this, as depicted by this diagram. It's totally taken from detailed 1969. You can have a highly weathered soil region on the top, followed by completely weathered rocks or still soil with some rocks in it, and to highly weathered, and finally to the unweathered and fresh rocks. But because of our weathering is very deep, so this soil layer can be actually very thick. Anyway, I mean, if you talk about zone 1, 2, 3, or 6, 4, 5, and 4 to be considered as soil, that can be in the range of many meters, and even up to probably 100 meters down. So that soil profile can be quite thick. Okay. Now, the adult soil have so-called transported soils. As I said earlier, the transported soils are basically soils that have been moved from the what we call the parent location to a different place. So these soils are what we normally call as alluvial, and they are normally found in engineering. That's because many of our structures are actually built along the coast, because most people tend to live along the coast. So, and they often fall into the category of subsoil because of their very low strength and also very high compressibility. And then we come to this very special type of subsoil, what we call peat, which I think in Japan you find there's a strong group doing peat research in the Hokkaido island. Right? So peat organic soil, a very special type of soil. By definition, well, it's not quite soil by the way, because it contains a lot of organic matters. So anything with 75% organic matter we call peat, but soil with more than 20% of organic matters we call it organic soils. Right? So peat and organic soil represent an extreme form of very soft soil. So these are problematic because they're subject to instability such as localized sinking or slip failure, massive family and even long-term settlement. Even on these land subjected even to a very moderate increase in load. So this is an example of a diagram to show what will happen if you build a house on peat. So because the house is built on steel, everything seems to be okay, but the surrounding area is not constructed properly or not treated will suffer massive settlement like this. Then come to, so basically about 30 million hectares of tropical peat are found in Southeast Asia. And in terms of thickness, it can vary from few meters to quite deep down. So this is just an example of peat distribution. So this is West Malaysia, this is East Malaysia, and significant amount of peat also found in Indonesia. Okay, is soil a problem? Well, people say, well, it's not soil a problem, but we probably don't understand what soil is all about. So these are just examples of some of the problems by the common associated with soil ground in Malaysia. This is our equivalent of Leaning Tower of Pisa. This is just a water tank. It's a Chinese-like, Japanese-like structure, but actually there's a water tank on top. It also tilts to one side. But because we're not good at marketing it, so we're not as good as the Italians, so it doesn't become really a tourist attraction. Here are some examples of houses being built on peat. You can see the damage to the house, and also this is a bridge that failures on the very soft ground. Okay, that's one problem. The second problem we have is a landslide. Now, soft ground is of course along the coast and toward the interior we have the restoral soils. Restoral soils are good in terms of foundation, etc. But they have another problem. We have the landslide problem because we have a very heavy rain. Okay, fortunately we don't have much in terms of earthquake in Malaysia, but we still have a lot of rain. So of course we all know that landslide, albeit rainfall induced, earthquake induced, are serious geologic hazard common to many countries. And for example, in our case, since 1975, we have more or less 400 landslides, and some of it are quite major and kills quite a number of people. Alright. So here are some of the landslide-prone areas in the country, just marked in red. But of course, this is not really the true picture of landslide distribution. What happened to those areas in red are basically the developed areas, mostly along towns and roads and something like that. Of course, we know landslide occurs everywhere, but those that occurs naturally in hills where nobody lives is probably of any interest to anyone. Okay. Now, just to give some example of our landmark landslide incident, this is an 11-story tower block that collapsed in 1993, and 48 people died in this particular incident. This is a mudslide. You can see the whole island is being weaved out because of the mudslide. 40 people died. And some of the most recent landslide in 2008, and in fact the most recent one is in November 2011 very near to Kuala Lumpur. Okay, so I just want to describe very quickly some of the work that we've been doing for our country in particular. I'll start with peat. So I've said actually peat or extreme example of soft ground, and go really into that. This is we've been working on some aspect of peat, for example, on the stabilization of peat. So we start with a shallow surface stabilization, followed by deep stabilization, and then we are interested in the electro-osmosis, and of late we are looking into electro-biography. So this is an example of different peat, depending on their degree of unification under the electron microscope, scanning electron micrograph. This is a very fibrous peat. This is the somewhere in the middle, not so fibrous, and this is the most decomposed or the septic peat. Alright. So first we start with stellar stabilization. So the effect of adding various percentage of chemical binders, because we all know that very important cement from 5 to 50%, to 8. Look at that. Also we add some additive like fiber, steel fiber, silica fume, ground granulated flash, furnace like fly ash investigated to study the strength of the peat. So for binding agent, because cement is the most commonly used material, in terms of reaction, they will produce calcium silicate hydrate, so calcium hydroxide. So the CSL gel has strong cementing effect and can dissolve particles together. For additive, additive are material other than water aggregate, which is added to the mixture or before or during the mixing procedures. So they can be chemically active, non-reactive. Advantage, of course, will improve the strength, more durable, and safe in terms of amount of the mixing agent in the mixture. Example of additive that we're looking at is like polypropylene fiber, steel fiber, silica fume, microsilica, BFS, blast furnace slag, as well as the fly ash. So this is just an example of some additive. This is the polypropylene fiber, some steel fiber, silica fume, fly ash, and also the BFS. Okay. The test is a common laboratory test. We have you as expect, right? So this is we have a large tank. This is the row cell. And thermal curing method, we look into various methods, moist curing with surcharge, as well as just air curing. So here are some examples of the uncombined compressive strength of untreated and of the what we call cement added fibrous peat. Okay, I won't go very detailed. This is an example of CDR of peat with and without polypropylene fiber. And this is an example of CDR of treated, untreated fibrous peat with cement and fuel ash after 3 months of curing. So, of course, in general, adding the chemical additive as expected proved to have increased soil strength substantially. Addition additive are beneficial, except for blast furnace slag and fly ash, where there appear to be no additional gain. Hay curing was found to be generally better than moist curing, and the best additive was from the polypropylene fiber with about 0.15% or 1.5 kilogram fiber per cubic meter of heat in its natural water content. Next, we look at code. Well, practically, shallow sterilization is not something that we would use for most practical applications. Obviously, if you're interested for some kind of real treatment, so probably the deep sterilization technique is the one which is a bit better off. So we start looking at the deep sterilization involving installing of columns, pit with cement, and additive into a pre-bored hole, set pit sample. So basically, this is what done. So in a simple lab test, we have a pit column, and then we pre-bore a hole in the middle, and we insert a pit cement column. All right, this is how the making was done. All right. Okay, here's some of the results. Because as we expect, to increase the amount of cement, obviously the strength and cohesion and cohesion angle also increases, and the compressibility, characteristic of pit decreases. Okay, and this is just the stress-strain relationship. All right, so in general, it was found the cement column improved both the shear strength and also compressibility reduction in capacity of pit, in particular with higher ratios of cement, and the low cement content in treated soil showed a ductile stress-strain relationship, and with an increase in cement content was a change from a ductile to a brittle one, with an increase in the soil strength. The high cation exchange CC capacity and humidification may also be the reason for high increase in strength of septic pit. This is the most decomposed pit compared with handling and deep fabric pit. And factors affecting the stabilized organic soils such as pit therefore dependent on water content, chemical, mineralogical properties, nature and amount of organic content, as well as the pH. So, but the addition of cement as well as the air curing found to be the most significant. Significant. This is just a large scale test that we did. I mean, not very large, but it was a tank of about 0.82 of a meter times 6 meter high, and we used to simulate the installation of this pit cement column. All right. So here are the results. Of course, as we expected, the soil treated with the column we performed much better than the what we call the untreated or the control sample. And this is another example of the loading and unloading curve. So this is the treated sample, large scale sample, and this is the untreated sample. Okay. So cement column made ordinary pit with additives such as polycarbonate fiber, silica fume that we found to be good in the first place. It's shown as beneficial improvement in improving the shear strength and compressibility of the pit. Of course, now then again there is a practical consideration. How do we install the cement column in pit? Well, if it's a shallow sterilization, or probably shallow deep sterilization, probably 3 meters, that's probably feasible. But if you want to treat, for example, 10, 15 meters of ground, that's not likely going technique to use. So then we look at the other possibility of using what we call the deep mixing method, deep mixing technology. Well, of course, we know that the DMM is quite well used for soft clays, but we are also trying to improvise this technique as far as for application of pit. So this leads us to the idea of installing some pit column, but in between we have a vacuum well. Let me explain why this is done. So this is just an example of a model that we do. This is a tank. I think so 1 by 1 meter, and we have a pit column and also the vacuum cell in between. The reasons like this, in terms of the quantity of pit soil is not that high. So when we apply the vacuum and at the same time installing the column, so it will have to speed up this sterilization process. That's one. Secondly is the low strength of the loose material pit mean we cannot use a high injection pump. So in this method, in this way, we can only apply a low power vacuum, low power injection. So they have to combination of the low power injection and the vacuum to help to spread the binder. So in comparison with the conventional vacuum method and the preloading, this method is believed to be more cost effective. So the effective error ratio should be higher, and there's no need to lower the groundwater level. Now, next, of course, the question: what sort of binder would we use? Now, sodium silicate grout, for example, is the most popular grout because of the safety and environmental compatibility. There are many varieties of sodium silicate system. I listed there 4, and from our study, we finally choose the sodium silicate amide as the grouting suitable binder for cement. So from this finding, using the sodium silicate and cement, we found that we call the injection, vacuum injection method, are able to increase the shear strength of the peat soil by about 50% compared to just injection alone. This finding agrees well with the final analysis as well as the pocket spectrometer. I'm not going to read the rest of the slide. So that's about what we have done. And in 2007, we began to look at another technique which is called electroosmosis. Basically, we're interested to know what is the role of organic matter on electroosmotic properties of peat soil or peat, and to investigate the electroosmotic flow of peat. So, as we know that electroosmosis is defined as a fluid movement with respect to a solid wall as a result of applied electrical potential gradient that is in direct current. We have one cathode, one electrode. So that's what electroosmosis is all about. So electroosmosis basically involved in water transport from a continuous or particle network, where the movement is primarily generated in the diffuse double layer of moisture film, where the cations dominate. Right? So unlike crystalline salts, clays, and so on, the electroosmotic properties of peat is not quite known, and the variation of peat arises from a number of factors such as the variety of land, which will contribute to the peat formation, as well as from the environmental condition in which the unification takes place. So here are some of the results of our test, and this is not the properties yet. We look at the limit of any contained CVC relationship. And some of the point, natural water contained liquid limit and cation exchange capacity, and the specific surface area of peat was found to increase in organic content, and soil with higher CVC has higher specific surface area, which provide the present more ion. And since a very wet soil mass in the present of ion, a suitable environment for applying electrical potential across the mass, therefore peat provide a good candidate for the electroosmosis technique. So this is some of the results of the delta potential with the pH as well as the degree of unifications, and this just shows the equipment that we made. It's not very complicated, just a peat sample in the middle with 2 electrodes on side. Okay. And here are some of the results that we obtained in terms of shear strength. For example, we found that on post peat is more sensitive due to the quantity as well as the quality of the charge. So in general, the shear strength of the peat decreases at the anode over here because of the acidic conditions. So in terms of the findings, we found that the electroosmosis properties of peat hinge on a number of factors such as cation exchange capacity, delta potential, specific surface area, as well as the degree of unification. And we just summarize here, for example, the electroosmotic coefficient increases if the unification increases, the pH increases, the surface charge increases, delta potential increases with organic content as well as unification. And dewatering is therefore quite effective after the EK treatment. And currently we begin to look at the new phase of work, which is what is known as biogrouting. This is a method to improve geotechnical properties of soils using bacteria, and we know that some bacteria has a potential to produce urease enzyme. So this enzyme is particularly able to hydrolyze urea to ammonia and carbonate. So the produced carbonate ion participate in the present calcium ion as calcium crystal, which they form cement in the soil particles. So what we believe the main motivation of this work is, since urease enzyme and bacteria are negatively surface charged, EK could probably transport bacteria towards the electrode and therefore distribute them uniformly in the porous medium soil. So what we're trying to do is use the EK technique basically to try to transport the bacteria. Okay? So that's new. Next, I move to the other type of soils, called the reservoir soils, and we begin looking at this this in 1991. Of course, I would say landslide is a problem in our country. What we're concerned is, I'd like to know what caused the landslide and landslide be prepared. We have a book on that in 2008. I'm talking about that. So basically, we have looked at various things like slope assessment system for predicting landslide, low cost repair of the slope using escape tires, that's done, and the use of the bioengineering for splashing slope. We've done that since 2007, and of late we're looking at effect acid rain. So I'm going to talk about these two points, the bioengineering and also the effect of acid rain. Okay, what is bioengineering for stabilizing slopes? Of course, we all know that trees do grow very well on slope, but the normal trees tend to be tall, so because of that, although they have a good effect in the root behind the slope, but because being tall, they also have a destabilizing effect on the slope. So the idea is, if we can find some species of trees that we can plant in a very close spacing, and not only in that, but also deep into the slope, this will be useful in terms of immediate as well as long-term slope stabilization. So the whole idea of right pole is basically to involve planting the woody stem, 50-80 millimeter of selected plant species, say half to 1 meter, up to 2 to 3 meter into a pre-drilled hole inside the slope. Right? So the benefit should be the environment, hydrology, as well as mechanical. So the challenge is to find what would be a suitable plant for this slope, of this type of application. So for our search, we end up looking at some sort of 10, 11 species that might be useful for this technique, and we finally end up having 3 species, which is the hibiscus, the delinia, and 2 types of delinia. Now, of course, we got to try ourselves the technique, because in the normal horticulture, we don't plant, we don't normally plant trees like this. I mean, people either use so-called bole planting, or you plant from the seed, but nobody will try to plant a pole into the ground. So what does it mean? Does it be first we start with the laboratory test. Basically, we call it shade house experiment. Where we have boxes like this, about 300 by 300 millimeter cross section to 1 meter deep, and then we insert in the pole. All right. So this is an example of the pole that we planted. So first, the pole must be able to grow, and secondly, it must have roots all along. Okay? That's the criteria to be selected as the light pole. Right? So this just to show that the 3 species, if you can find them in the wild. Mechanical test, I described that. We have also to make our own big shear box, because this is to take this is a 300 by 300 millimeter sample with the root. All right. And also measure sun suction. Of course, we know that the added benefit of vegetation is not only has a root, but it also improves the soil suction. Okay. After having found these 3 species, so we have to try whether it works on the slope. So this is particular slope that we have chosen. It's somewhere in the university campus. This is a very bad slope in terms of engineering. Actually, it's a very poor soil, very silty, scree soil. As you can see, it has been failing some failures. So, and this is an example of this is the trial that we've been doing. In fact, it was done in 2008. As you can see, we have to auger down a hole, and this is the sample of the light pole, the hibiscus, and also the delinia. And this is the series of planting down the slope, so you can see this, you can understand. Okay. All right. So this is the planting light pole. So each light pole was level, and then we also have a bit of irrigation system to make sure it survives with a bit of shade. Because we want to have one shot at the ground to make sure that the pole survives. Okay. And this is just a 2 example. This is a picture to show the 2 streaks, which is about 50 meter apart. Right? And this is what happened 3 months after planting. You can see it survives, it grows. 6 months, and about 1 year later we dig it out. So thankfully more than half of the pole is still okay, and you can see it has roots all along, right? But the leaf are being eaten by insects, but we did not apply any insecticide whatsoever. Okay? So I took this picture 1.5 years later. during a rainy day. I think you can see just about see the rain. Okay, and you see the lateral section still to be okay, and the rest of the slope has failed again. Alright. So light pole was apparently effective against the rising slope. Again, shallow failures, and it's good, particularly if you put them in a very close area and soil at higher original coefficients. And we begin to look at the effect of acid rains. As we know that acid rain refers to any kind of precipitation, mist, fog, or of course rain, that are more acidic than normal. So basically it's caused by sulfur dioxide and nitrous oxide. Of course we all know this, it is from the factory, from cars and so on. So this chemical are converted to sulfuric acid and nitric acid in the atmosphere and can be carried by wind for many kilometers. So microstructure changes are often responsible for the strength change in deposited clay rich soil. So many slopes at metastable state and relatively minor change in the loading condition is sufficient to bring them down. So the objective of this study is to investigate the fundamental principle and mechanism in ground acid rain and soil strength parameters, and to assess the possibility effect of the acid on the landslide, and as well as to make recommendation. Well, of course, this is a hypothesis, but we think that the acid rain particularly would attack certain types of clay soils in the slope, and therefore would help to increase the chances of the slope to come down because of the landslide. So I think I'm just about done. So thank you very much. Thank you.
Do you have any questions?
Thank you very much for your presentation. And I'm Hiroyasu Ishii from Japan. And your live poll was the most interesting to me. And just I want to ask you, do you have any idea for design? Because just I thought it was natural reinforcement pile. We can apply the conventional design to this idea. Just I thought that. Do you have any comment for design?
You see the light bulb?
Yeah.
Okay. When our light bulb in the short term acts as a short balance, because we can plant it, we can insert it down maybe up to 2 meters down. So over time we should grow roots, so that will give you an added reinforcement. And also, as we know that because it is living, you take away water from the soil, but that will actually increase in suction. So you have 3 benefits. One, the pole acts as a shear pile. Secondly, you have the root, which improves the soil. And third, you have the added benefit of the suction. But of course, light pole is only used for shallow stabilization. It's not good for any kind of deep landslide. But for surface landslide, shallow landslide, it is a good technique. And not also to mention other environmental effects, because as we know nowadays, we have only cars and factories. We should have more environmental friendly. Trees are good because they take in the carbon dioxide and therefore help to reduce the greenhouse effect. So I think that is a good benefit of this direction. But of course the design is not so easy because I think we are still struggling with how to design slope, for example, incorporating all the effect of root suction. Does that answer your question? I saw there's one slide, a poster outside. I think they're quite interested in using trees as well.
Thank you very much. I understand it. Not so simple.
Not so simple. Although qualitatively we know all the benefit. Quantitatively it's quite hard to explain.
Thank you very much.
Most welcome.
So that's it.
Thank you.
It's coming, so thank you very much.
You're welcome. Thank you.
So I'd like to close this sessions. So I moved lunchtime. So Thank you very much for the speakers and the participants. So thank you very much.